Chapter 8, we just finished the first part of 8.2. When the equation is when the equation satisfies the self-adjoint condition, so the operator is L times psi, operator on psi, and this L operator is this P sub 0 E squared d x squared plus P sub 1 e dx plus P sub 2 then nothing. The P sub 0, 1, and 2, they are function of x and then operator side. Right, so that is the form, assuming of this form, and then the self-adjoint condition is this 1 equals to P sub 1. If that is the case, then this implied L is this. You can combine the first two terms to be P sub 0, and then that's P sub 2. Right. You can check that this is the same. And last time we showed that if for this form, if you define your scalar product, say whatever symbol you use, G is integrating over the domain of the function, so you A to B, complex conjugate G. If you define that this is your form of your scalar product, then this form of operator will satisfy, I think, that's what you U and U, V and U, V and U, the L operator on U is equals to L operator on V. They satisfy the self-adjoint condition. So normally we define that this equals to the adjoint operator on V and the scalar product with U. But that now, if for this kind of operator, you show that this equals to that, provided the boundary terms are 0. So the boundary terms are, I think, in the equation 8.12, if this boundary term you have V, P sub 0, actually you can take the P sub 0. If P sub 0, U pi minus U star pi U, evaluate A and B as 0. So if there's no boundary terms, so that 3 ways to satisfy that. So either the function is 0 at the boundary, so U and V are 0, that would be 0, or the derivative U pi and V pi are 0. So that would be the first case would be the Dirac boundary condition. The second is Neumann boundary condition. There's one more possibility is P0 at A and B is 0. So P0 doesn't have to be totally 0. Over totally 0, of course, that is you just reduced all the office there. But if P0 is a function of x and is 0 at A and B, then that is another possibility. As long as there's no boundary term, then this form of equation satisfies the self-adjoint condition. Okay, I mean this kind of scalar product is sure that it's self-adjoint. The adjoint operator is the same as the operator. Okay, and then the next discussion is when the operator, this P0 and P1 doesn't satisfy this one, doesn't satisfy this condition. And what we do to still define a self-adjoint operator, or to make the operator self-adjoint, but not with respect to this kind of scalar product. We actually need to multiply a weight function here, so you multiply by W, so that it becomes self-adjoint. So we do that. We repeat, kind of repeating the discussion last time in here, and define the scalar product with a weight function W and see what happens. So now this kind of scalar product will be that you have A and B, V. Now you multiply by a W. W now it's a function X also. And then you multiply the L here, LU. LU is here is 0. E square. This is this operates on U. This is 1. This is 2. U. Then you define your differential operator, define your scalar product with this kind of differential operator, not satisfying the self-adjoint condition at first, and you hope to get to something like that with this with your choice of W. And what you want is basically require W, set W such that this form will go to a new form. See, let's continue here. A and B. We absorb the W in the differential operator, W is 0. B square U X squared plus W is 1 into X is 2 U W is 2 U. Right. And then you require that your new coefficient, now you call it, you can define it differently. I think a textbook call it a P sub 0 bar. It doesn't matter whatever you call it. P sub 1 bar. Okay. And this one doesn't matter. This one is always self-adjoint, P sub 2, because it's just an ordinary product, so it always you can interchange U and V. Okay. And you require that this P sub 0 bar and P sub 1 bar satisfy this kind of the original definition of self-adjoint. So you require that the P0 bar prime, which is W P sub 0 prime, equals to P sub 1 bar, which is W 1. Right. And now this is a differential equation for W. You can work that out. W prime P0, and then you have a P0 times P0 prime times W, and then you have P1 also, and you can move the other term over there, so it equals to W is 1 minus P0 prime. Right, and that is a very simple differential equation for W. We can just solve it. You move W here and integrate that. That becomes a log function, log W. Right, and divide that to the other side and integrate that. So the solution is quite trivial. W is just exponential of integration P1 minus P0 and divided by P0, right, and dx. Right, and this is, we are intentionally not fixing the limit, so it means this is like a independent, an indefinite integral. So, and then supposedly you have a constant, but the constant just can absorb into the proportionality constant of W, because exponential constant is still a constant. It just means that you have an arbitrary choice of constant in front. And then one more thing is the second term is PCO pi divided by PCO, which is log PCO pi, right? And that integrate log P0, right? It means this is minus or log P0 or plus log of 1 over P0, and exponential function of that would make it 1 over P0. And then the other factor is just keep it like that, P0. B1 divided P0. Right. That would be your choice of your W. I think that is your equation 8.15. Right. So once you choose W to this form, then you satisfy this equation. Basically, this equals to that, which is the same as the original one. And your scalar product, basically, now you reduce back to your the derivation we did last time. This is exactly the same derivation, except that you change P0 to P0 bar, P1 to P1 bar, P2 to W times P2, or you can say the P2 bar. So P2 bar doesn't matter. So everything went through, right? And that you can show that by what we did last time. So just follow exactly the same integration by part 2 times, and you see that this is equals to, right? Yes, to have space here. This is equals to, just like what we did last time, A and B is interchange U and V. So U, and then well, I forgot this. There's a complex conjugate. When you define the scalar product, there's a complex conjugate. Okay, U, and then this PCO bar P square V star dx square plus P1 bar V dx P2 bar. Yeah. Just like what we did last time. Just now, you can show the n plus the boundary term. Now you have the boundary term is just like here, just like this one. You have P1 bar, and then pi, V star, pi, okay. So this will be self-adjoint. This will be self-adjoint. Now you can substitute back this PCO bar, P1 bar, P2 bar back to the PCO. This is just the original operator multiplied by W. So this is like your definition of scalar product with a W using the original differential operator. So this term, this the first term is just this is this operator V on the left-hand side is operator V. Provided that the boundary terms is 0. And again, the three ways to make it zero. Either the functions are zero, u and v are zero at a and b. That's the theory K boundary condition. And then the next possibility is the derivative u prime or v prime. U prime and v primes are zero at a and b. So that Neumann boundary condition. And the third one is P1 bar is zero. So P1 bar, so no, this is P0 bar. So this is P0 bar. This is probably P0 bar. The P0 bar is W times P0. So now becomes P0 times W is zero at the A and B. So there are three possibilities. And it's the combination. Sometimes maybe P sub 0 is non-zero, but multiplied by W becomes zero, or vice versa. So the combination, the product, as long as the product is zero at A and B, so therefore the three possibility to make the boundary term to zero, and then you have the self-adjoint condition. But this self-adjoint is again is based on the scalar product with a W. So the whole thing is now is just if the original differential operator doesn't satisfy the self-adjoint condition, so you just calculate W and define your scalar product with a W in the integram, okay? And then the one condition, of course, when you define a scalar product, we already mentioned that W must not be negative, so it can be zero at isolated point, but it must be positive otherwise. And from here, from this condition, so you can say that it's positive because the original is exponential function. I mean, after you integrate that, that looks like there's a P sub 0 coming out, but that's because we are not keeping all the constant. But when you do the integration, you most likely get the W that is positive definite, except isolated point. So that would be enough to make sure that the scalar product is well defined. If the scalar product becomes negative, then it's not what we want. Because we use scalar product sometimes we use scalar product to normalize your function also. You don't want the scalar product becomes negative. Okay, so that is this discussion. Basically, the whole idea is you have the arbitrary differential operator. So depends on whether it satisfies the self-adjoint condition. You need to insert a weight function in the definition of the scalar product. Okay, so if you satisfy the self-adjoint condition, obviously W will be 1, like that. If you satisfy, so you can say that if P1 is just P0 prime, right? That obviously that will make it a log P0 prime and integrate and be log P0. So that whole thing becomes P0 and cancel with the P0 becomes 1. Right, so that is obviously the reduce back to the original case. Okay, so that's the discussion of this W or the weight function. It's okay. So, all right, and there's one example following that, but it's very easy, so I won't go through that. But I think we assigned a couple exercise. So when you work on that, you know how to do it. And then the next section has another example that then we can work that out, the W for that example. Is okay? So, so that's 8.2. Any question on this section?